Hello, everyone. Today, we're diving into the physics of optics, specifically looking at thin lenses. We encounter these every day, in glasses, cameras, even our own eyes. We're going to break down exactly how they manipulate light to create images.
So first things first, what actually is a lens? At its core, it's just a piece of transparent material. But the magic happens because of refraction. When light hits the lens, it bends. Depending on the shape of that material, those light rays either come together, converge, or spread apart, diverge, to create an image.
We generally categorize lenses into two main families based on their shape. You have convex lenses, which bulge outwards, and concave lenses, which curve inwards. The shape is crucial because it dictates exactly what happens to the light passing through. Let's start with convex lenses. These are the classic shape you think of, thicker in the middle than at the edges. We call these converging lenses because they take parallel rays of light and bend them inward until they smash together at a single spot called the focal point. On the flip side, we have concave lenses. These are thinner in the middle, like an hourglass. Instead of focusing light, they scatter it. We call them diverging lenses because the rays spread out lighter. The focal point here is actually virtual. It's a theoretical point where the rays would meet if you trace them backwards, but the light doesn't actually go there.
Now, in the real world, light bends once when it enters the glass and again when it leaves. That's a lot of math involving Snell's law. So physicists use a cheat code called the thin lens model. We just assume all the bending happens instantly at the center line of the lens. It makes our calculations way cleaner.
When we draw ray diagrams for convex lenses, there are some hard rules. First, the focal length is always considered positive. If your object is far away, the image is real and upside down. But, and here's the cool part, if you bring the object really close inside the focal point, the image becomes right side up and huge. That's exactly how a magnifying glass works. Concave lenses are much simpler, thankfully. Their focal length is always negative, and no matter where you put the object, the result is the same. The image will always be virtual, it will always be upright, and it will always be smaller than the original object. No exceptions. Okay, let's talk math. We use two main formulas. The first connects the focal length, object distance, and image distance. The second calculates magnification. The tricky part here is the signs. Object distance is always positive, but image distance? That's positive for real images and negative for virtual ones. You have to watch those minus signs. Let's try a quick example. Say we have a convex lens. We put an object 20 centimeters away, and a real image forms 8 centimeters on the other side. We plug those into our thin lens equation, 1/8 plus 1/20, take the inverse, and we get a focal length of roughly 5.71 centimeters. Now, what does that image look like? We use the magnification formula. Negative image distance divided by object distance gives us negative 0.4. That minus sign tells us it's inverted, upside down, and the 0.4 means it's less than half the size of the original. So, real, inverted, and reduced. Let's do a concave one. Object is at 14 centimeters. The image is virtual, appearing at negative 10 centimeters. We plug that negative 10 into the formula carefully. When you crunch the numbers, you get a focal length of negative 35 centimeters. That negative focal length confirms it's a diverging lens. To wrap this up, remember that convex lenses converge light and have positive focal lengths, while concave lenses diverge light and have negative focal lengths. The thin lens model makes the math manageable, but you have to be disciplined with your positive and negative signs. Master those signs, and you've mastered lenses.